So this may be the last video of this chapter, physical spectroscopy. In physical spectroscopy, we have already mentioned that we will cover the major topics. One is rotational spectroscopy, vibrational spectroscopy, rotational vibrational spectroscopy, and finally Raman spectroscopy. And these three topics we have already covered in our previous video. So in this video we will cover Raman spectroscopy. So now let's go to Raman spectroscopy in detail. In Raman spectroscopy, the radiation, electromagnetic radiation we are using is UV visible radiation in the form of laser light. Laser light means it is very highly pointed or directional, we can say. So UV visible radiation is used here. That means when UV visible radiation incident on a molecule, major part of the radiation passes without any change, that means transmitted, and a little part can be scattered. So we can say that Raman spectroscopy, we will study the scattering of UV visible radiation when the radiation incident on the molecule, if and only if the molecule is Raman active. The molecular vibration is Raman active. Molecular vibration is Raman active. So now we have to consider how to check whether a molecular vibration is Raman active or not. So the selection rule we are using to find a molecule is some spectroscopically active or not. That selection rule is known as gross selection rule. And for rotational spectroscopy, we have already said that if a molecule to be rotationally active, it should have some permanent dipole moment. That is the gross selection rule for a rotational spectroscopy. And for a molecular vibration to be vibrational active or IR active, in the case of vibration, we are considering the vibrational modes. Different vibrational modes are taking into consideration, and we are checking whether that mode is active, vibrationally active or not, IR active or not. That means whether that mode gives a spectral line in IR spectroscopy. For that, we said that we will check whether there occur a change in dipole moment during that particular vibration. So this was the selection rule for vibrational spectroscopy. And when we come to the Raman spectroscopy, the gross selection rule is there should be a change in polarizability during the vibration. So Raman spectroscopy also somewhat related to vibrational spectroscopy. Here also we are considering some vibrational modes, and we are checking that whether there occur some change in polarizability or not. To know about the polarizability concept, there is a concept called ellipsoid, which is discussed in the book of Banwell's Molecular Spectroscopy. There it has written very in descriptive manner, so we are not going that much. We are using some easy version to understand whether a molecular vibration poses change in polarizability or not. So first of all, we have to know what is polarizability. Polarizability, we can say it's just opposite of getting neutralized. Neutralized means there is no charge. So polarizability means there is some charge difference, we can understand. That means if we are considering a non-polar molecule, we would say that the electron density is spread uniformly so that the molecule can be considered as a non-polar one, because it has both positive and negative charge, but they cancel somewhat and look like a neutral thing. But when a positive electric field is held near to this molecule, what will happen? The negative electron cloud may come near to this positive electric field, and we can see some sort of distortion in the electron density, just like this. So if this happens and negative charge come near positive electric field and positive charge go away from this positive electric field, Now this molecule, the earlier molecule which was in a neutralized form, now it is said to be polarized. So this is the concept of polarization. So now we have to consider the Raman spectroscopy thing, and whether the molecule have some change in polarizability during a particular vibration. For that we can say an easy method. Polarizability depends upon three factors. One is bond length, second one is bond angle, and third one is direction. So during the vibration, if bond length is changing, we can say there is a change in polarizability. If bond angle is changing, we can say there is a change in polarizability. Or if the direction of polarizability changes, then also we can say there is a net change in polarizability. Let's take an example and see. So when we take CO2 molecule, we have already discussed whether which all vibrational modes of CO2 are IR active or not. Here we are going to discuss which all modes are Raman active and not. So for that we have to consider all vibrational modes of CO2 molecule. So first we have to calculate how much vibrational modes CO2 molecule have. So CO2 is a linear molecule, we all know. For a linear molecule, total number of vibrational modes is equal to 3n minus 5, as it is a linear molecule. If it was a non-linear molecule, we are considering it would be 3n minus 6. We are considering 3n minus 5 because CO2 is a linear molecule. Then for n we will put number of atoms. Here 3 atoms are there, so 9 minus 5 we will get 4 total number of vibrational modes. In this 4 total number of vibrational modes, we are considering each of them. First one is symmetric stretching. With this we have already studied in the case of IR activity. Second one is asymmetric stretching. Third one is bending in plane. Fourth one is bending in out of plane. Let's first take first mode of vibration, that is symmetric stretching, and see whether it is Raman active or not. So symmetric stretching means first CO2 molecule was like this, and this we can say the midway structure, means the normal structure of CO2 molecule before vibration. And during the vibration there is two extremes possible. One is fully stretched, means bond length is increased in both sides, fully stretched, and another one is fully compressed where bond length is shortened, and this is the midway. These are the two extremes, stretched form, contracted form, or compressed form. So now we have to consider during this vibration means before it is in the stretched form, after it is in the compressed form. So we are only considering these two extreme states to know whether there occur a change in polarizability or not. So we have to check whether there occur a change in polarizability or not, and we have already said that this change in polarizability happens if there is any change in bond length, bond angle, or in the direction of polarizability. So first let's take bond length. So here the overall bond length of the molecule is this much, the total bond length we are considering, but after vibration or during the vibration it changes to this much small. That means there is a change in bond length. So if there is a change in bond length, we can say there is a change in polarizability. So this mode of vibration, that is this symmetric stretching mode of vibration of CO2 molecule, is Raman active. So what about the IR activity? IR activity we will check using the dipole moment concept. There also we are considering this expanded form and this contracted form. Here the dipole moment is 0 because both sides got cancelled, and here dipole moment is 0, and here also dipole moment is 0. So what we conclude, there is no change in dipole moment, because we have already said for vibrational spectroscopy we will consider the Grove selection rule of change in dipole moment. So there is no change in dipole moment. So this mode of vibration of CO2 molecule is IR inactive. So if we sum up the IR activity and Raman activity of CO2 molecule, let's take CO2 molecules, its Raman activity and IR activity we are comparing. And first we took the symmetric stretching mode of vibration. We saw that during the symmetric stretching the molecule is Raman active and IR inactive. Now we are taking the second mode of vibration, that is asymmetric stretching. In asymmetric stretching we know that this is the midway structure. The possibilities, if one atom going away from the bond, one is coming towards the bond, and just opposite happens here. This comes towards the bond and this go away the bond. So if we are taking the bond length, the total bond length is this much here. Same we can see here also. So the net bond length or overall bond length of the molecule during this vibration is same. That means there is no change in bond length. So next factor we have to consider is whether there is a change in bond angle. So bond angle also, it is visibly seen that there is no change in bond angle also, and there is no change in direction. But direction we don't have to consider. Direction we consider if the molecule is non-centrosymmetric, because for a centrosymmetric molecule, polarizability can be considered as a scalar quantity. Direction don't need to consider. But for a non-centrosymmetric molecule, we should consider the change in polarizability. Polarizability is a vector quantity and we should consider that. So as CO2 molecule is a centrosymmetric molecule, we don't have to bother about the change in direction. That we can more understand soon. So there is no change in bond length, so there is no change in bond angle also, which means the molecule is Raman inactive. So we can say the asymmetric stretching mode of CO2 molecule is Raman inactive. And now we have to check whether it is IR active or not. That we have already discussed. For IR activity we consider the dipole moment. So here the net dipole moment is towards this side, because this is the large part and this is the small part. So net dipole moment is left side. Here the net dipole moment is right side. So we say there is change in dipole moment, and dipole moment we consider as a vector quantity here. So we have to consider the direction. If x is the dipole moment here the dipole moment is minus x, just opposite direction. That we have to consider here. Dipole moment is always taken as a vector quantity. So there is a change in dipole moment. So we would say CO2 molecule asymmetric stretching is IR active. Now let's consider the third mode, because that is bending in plane. So bending in plane means this is our CO2 molecules. The first possibility is bending downwards. So this is the in plane of the molecule, or plane of the paper is the plane of the molecule. So then the other possibilities bond goes like this. So these are the two extreme possibility during the vibration. So we are considering this and this only, no midway structure. Extreme states are only considered while checking. So here we can say bond length is not changing. Same bond length during this time. The bond length is this much, and here also bond length same, no change in bond length. And if we are considering bond angle also same, no change in bond angle. So there is no change in bond angle also. Direction we don't have to consider, as it is a centrosymmetric molecule. So we will say that the bending in plane mode is Raman inactive. So for CO2 molecule, the third mode, that is bending in plane, is Raman inactive. So now we have to check the IR activity. For IR activity we are considering dipole moment. So as we can see from this figure, here the dipole moment is downward, here the dipole moment is upward. So there is change in dipole moment. So this mode is IR active. Now let's go to the fourth mode of vibration, that is bending out of plane. So if our CO2 molecule is in this plane, The out of plane means this plane. These things we have already covered during the vibrational spectroscopy lectures. So the molecule will go like this during the vibration. One possibility is this, another possibility is this. So here also there is no change in bond length, no change in bond angle. So this mode is also Raman inactive. And if we consider IR activity, the dipole moment is this direction here. Here the dipole moment is this direction. So there is change in dipole moment. So this fourth mode of vibration, that is bending out of plane, is Raman inactive and IR active. So only one mode, that is symmetric stretching mode of vibration, is Raman active. All other modes are Raman inactive for CO2 molecule. And one more thing we can see from here. Here the Raman activity and IR activity are complementary to each other. If that mode is Raman active, then it is showing IR inactive. If it is Raman inactive, it is IR active. If it is Raman inactive, IR active, inactive, active. So there is a complementary between Raman activity and IR activity, which is known as mutual exclusion principle. And this mutual exclusion principle is only for a centrosymmetric molecule. That means if the molecule is centrosymmetric, very important, if the molecule is centrosymmetric, if it's one of the vibrational mode is Raman inactive, then that mode should be IR active. If the vibrational mode is Raman active, it should be IR inactive. That means IR activity and Raman activity of a particular mode of vibration for a centrosymmetric molecule is complementary to each other. This is known as mutual exclusion principle, and this is only applicable for a centrosymmetric molecule. Now let's check the Raman and IR activity of H2O molecule. H2O molecule, we know that it is a nonlinear molecule. So total number of vibrational modes is equal to 3n minus 6. That means 9 minus 6, 3. Which are the three modes of vibration? First one is symmetric stretching. Second one is asymmetric stretching. Third one is bending in plane. So first let's consider symmetric stretching mode of vibration of H2O molecule. So if this is the midway structure of H2O molecule, the two extreme possibilities during symmetric stretching is both bonds lengthen, both bonds shorten. Then we are considering these two states to check whether it is Raman active or not. So we can visibly see that there is a change in bond length. Here the total bond length is higher, here the total bond length is lower. So there is a change in bond length, which means there is a change in polarizability, so that the molecule is Raman active. So if we are also consider this comparison for H2O molecule, we found that symmetric stretching mode of H2O molecule is Raman active. Now let's also remind the vibrational activity. Vibrational activity, here dipole moment is towards downwards, here also downwards, but the magnitude is changing. That means there is a change in dipole moment. Accordingly, that vibration of H2O molecule is IR active. So here you can see there is no complementary result obtaining. If it is Raman active, there is chance for IR activities also. So that is because this H2O is not a centrosymmetric molecule. It is not a centrosymmetric, it's a non-centrosymmetric molecule. So mutual exclusion principle cannot be obeyed. Now we are going to other mode of vibration, that is asymmetric stretching. In asymmetric stretching, if one bond lengthen, one is shortened. For here the opposite is this bond is shortened and this bond is lengthened. So here we can see that the total net or not total bond length is same. Here we can say this much is the bond length, and here also same bond length, total bond length is same. So we cannot say that bond length is changing. That means bond length is constant. It's not changing actually. So bond length is not changing. So bond angle also, if we consider, we can understand bond angle is also not changing. Same for both cases. But here what is changing is direction of polarizability. You can visibly see that this shape is just opposite of this thing. So that affects the electron cloud distortion also. So here what changing is the direction, and we have to consider the direction of polarizability as it is a non-center of symmetric molecule, and we can say that this mode is Raman active. So considering IR activity, we are seeing the dipole moment. Here net dipole moment is towards this side, here net dipole moment is towards this side. So both dipole moment are different, direction is different, so dipole moment itself is different. So there is change in dipole moment. So this mode is IR active also. Here also we get both Raman and IR active. And now we go to third, that is bending in plane. Third and last mode of vibration for H2O molecule. Bending in plane means first if the molecule is like this, the other condition is molecule bond angle changed. This type of vibration occur. So here bond length is same for both the cases. Bond length is not changing. What changing is bond angle. Here bond angle is higher, here bond angle is lower. So bond angle is changing. So there is a change in polarizability, and this mode is also Raman active. And coming to IR activity, dipole moment is like this. Here also dipole moment is changing, so that this is IR active also. So we can write here the third bending in plane mode is also both IR and Raman active. So for H2O molecule, all the modes are Raman active and IR active also. But when we do experimentally the Raman spectroscopy, the result may change from this theoretical explanation. So this is the way to check whether a molecule is Raman active or not. We have to, not a molecule, for a particular vibration is Raman active or not, we are checking using change in polarizability technique. And this polarizability depends upon change in bond length, change in bond angle, and change in direction of polarization. Now we are going to the spectral part of Raman spectroscopy. So the electromagnetic radiation, as we have already mentioned, we are using UV visible radiation. We know there are total 7 electromagnetic radiation: gamma ray, X-ray, UV, visible, IR, microwave and radio wave, and each is particularly used for several different spectroscopies. Gamma radiation is used in Mossberg spectroscopy. X-ray is used to study X-ray diffraction of crystals, XRD technique, and UV visible spectroscopy mainly used to as an electronic spectroscopy that we will cover in coordination chemistry, how molecules shows electronic spectroscopy. And as we mentioned here, the UV visible is the radiation we used in Raman spectroscopy also. IR radiation is used in vibrational spectroscopy, micro is used in rotational spectroscopy, radio in NMR spectroscopy. So this is one of the basic idea of spectroscopy part. Other important part of spectroscopy, in every spectrum we are plotting either lambda wavelength, which has a unit centimeter, nanometer, etc., or we can plot energy in x-axis, which is equal to nu bar. Actually we know energy is equal to h nu, but during considering the spectroscopy we take energy as nu bar, which is the reciprocal of wavelength, so that the unit is centimeter inverse. and in y-axis what we are seeing is intensity or absorbance, and that depends upon number of transitions with that. But if we are obtaining a peak like this, that means within this, using this energy, a particular transition is occurring, and how much number of transition occur, as much as the number increases, the intensity increases. So intensity depends upon number of transitions rule, which depends upon the selection rules, which are the allowed transition. If it is allowed, the number of transition will be high. If it is a forbidden, it is very low, like that. So in Raman spectroscopy, we are mainly considering the scattering of UV visible radiation. Scattering means there is a change in the path of the light. So if this is our molecule, which is Raman active, and we are hitting UV visible radiation, most of the radiation goes without any deviation, which is considered as transmission, and some part of this radiation may get scattered back. And in Raman spectroscopy, we study this scattering effect of radiation by molecule, and from which we are studying the chemical nature of the molecule or chemical bonds involved in the particular molecule by analyzing the energy of this scattered radiation. ES indicate energy of scattered radiation. So for transmission, we know that the energy is same. But for scattering, there is two possibilities. Scattering can be take place like there is with change in energy. That means the energy of incident radiation is same as energy of scattered radiation. That means if some radiation comes with particular energy and scatter with that same energy, there is no net loss or net addition. Both are same. Incident energy and scattered energy is same. And another possibility, of course, they are different, not equal. So this type of scattering is known as Rayleigh scattering, and which cause Rayleigh lines in the spectrum. This is known as Rayleigh scattering or elastic scattering. And if it is not equal, it is known as Raman scattering, which is useful in Raman spectroscopy to study the nature of bonds. And in Raman spectroscopy, also known as Raman scattering or inelastic scattering. In inelastic scattering, there is two possibilities. If it is not equal, that means either EI can be greater to ES or EI can be smaller to ES. Two possibilities are there. If ES is smaller, it will result in stalk lines in the Raman spectra. Stalk lines. If ES is higher, that means energy of scattered radiation is higher compared to incident, that will give anti-stalk lines in Raman spectra. This I study with a technique that if ES is small, the line is small. That means there is stalk and anti-stalk, which is the bigger word. Stalk is the smaller word and anti-stalk is the bigger word. Bigger word means energy is bigger, scattered energy is bigger. Small word means energy of scattered radiation is small. This is the way we should remember things. Now let's see these things in the vibrational levels. We are considering different vibrational levels. So in Raman spectroscopy also the levels we are considering are vibrational energy levels. V equal to 0, V equal to 1, V equal to 2, V equal to 3. Such levels we are considering. Vibrational energy levels are considering. So during initial time, our molecule is in the ground state. This is our molecule which is staying at the ground state. If we are giving some energy, that is UV visible radiation, it absorbs that energy and go to some higher level, any higher level, let's say, and immediately it will come back from that higher level, so that in that higher energy level they stay for a very short period, so that we are considering it is a virtual level. It's an imaginary level, just going, and maybe it is not there. Just for consideration, we are considering it as a virtual level, and immediately it come back to the ground state. So what we are seeing is the energy absorbed is completely emitted during the jumping of molecule back to the ground state. That means energy incident is equal to energy emitted. And another possibility is the molecule in ground state and going to the higher level, and it may jump but not to the same ground state but one level above. That means it absorbed some radiation called EI, incident radiation, and it didn't emitted it fully. Some part the molecule absorbed and a very small part not a complete part, small part is emitted. So this is the energy of emitted radiation or scattered radiation. So here we are seeing that energy of scattered ray is smaller than energy incident. So this is the condition which result in Stokes lines. Smaller the energy of scatter, small word, Stokes lines. So how anti-Stokes lines are formed? Which transitions cause anti-Stokes lines? If energy of scattered is higher than energy of incident, how it can be drawn? It should be like this. The molecule starts from a higher level and reaches the virtual state and jump to a level lower than, not a level, some level lower than the initial level. So that what we are seeing, this is the energy of incident radiation. This much is the energy of incident radiation, but this much is the energy of emitted or scattered radiation. So we can say that which is scattered radiation is greater than incident radiation. So this first condition is called Rayleigh scattering, which results in Rayleigh lines where there is no change in energy, but here yes and EI are not equal and there is some difference in this energy, and this difference is called known as delta E, which is known as Raman shift. So for Stokes lines, Raman shift is E scattered minus E incident. This is known as the delta E. For anti-Stokes lines, ES is greater, so ES minus EI is the delta E, and for Stokes lines, EI minus ES is the delta E, which is called Raman shift. So by looking this Raman shift, we can analyze the chemical structure and chemical bonds of a molecule. Next we are going to study rotational Raman spectroscopy. That means rotational spectroscopy and Raman spectroscopy in a combined form. Here we have to study the selection rules for this rotational Raman spectroscopy. So the selection rule is like this. For a molecule, if a molecule is showing rotational Raman spectroscopy, the transition is using the format delta J equal to 0 and plus or minus 2. That means the transition occur in a way that delta J is equal to 0 or plus or minus 2. So we have to consider the delta E or energy required for this transition. So we know that for an energy level EJ, for an energy level J, the energy is EJ is equal to BJ into J plus 1. This we have already studied in rotational spectroscopy. So if we are considering a transition from J to J plus 2, because here the selection rule for rotational Raman spectroscopy, the selection rule is delta J should be equal to 0 or plus or minus 2. So 0 means if it is, let's draw a picture. So we are considering rotational levels during Raman vibrations. J equal to 0, J equal to 1, J equal to 2, J equal to 3, etc. So delta J equal to 0 means if it starts from 0 and come back to 0 itself. And J equal to plus 2. J equal to plus 2 means final minus initial should be equal to plus 2. This is possible when a transition from 2 to 0 or 3 to 1, 2 to, final should be 2. That means transition from 0 to 2. So that 2 minus 0 we will get plus 2. if we need delta J is equal to plus 2, the transitions are 0 to 2. So that final minus initial, 2 minus 0 is plus 2. And 1 to 3, 2 to 4, these are the transition which causes delta J as plus 2. For delta J minus 2, the transition is just opposite. Minus 2 means 2 to 0. So that J final minus J initial. J final is 0 minus J initial is 2. Delta J is minus 2. So 2 to 0, 3 to 1, 4 to 2. These are the transitions. Let's just draw here. So this type of Rayleigh scattering causes delta J is equal to 0. And delta J equal to 2 means plus 2 means 0 to 2. Delta J equal to plus 2 means 0 to 2. Starting from 0 and come back to 2. Like that 1, 2, 3, 2 to 4. So this will give stock or anti-stock. This will give stock line. That means delta J equal to plus 2 is responsible for stock lines. The transitions with the delta J is equal to plus 2 is responsible for stock lines. And if we consider anti-stock lines, what happens? It starts from 1, not from 1, it starts from 2. It's a mistake, sorry. It starts from 2 and reaches 0. Starts from J equal to 2 level and reaches 0. So here is a mistake. Here this reaches in J equal to 2 level. And here start from 2 and reaches 0. So which will give anti-stock lines. Now we have to consider the energy required for this type of transitions. So first delta J equal to 0. For delta J equal to 0 transition, there is no need of extra energy we have to provide. And if we consider delta J is equal to plus 2. So the energy required is 0 here, let's say. Energy required from J to J, same level. The transition is between same level. J to J level is 0. And if we are considering delta J equal to plus 2, which gives stock lines in the spectra, we have to find what is the energy required for that type of transition. So here we know that the transition is from J to J plus 2 transition we are considering. So we know that the energy of jth level Ej is equal to Bj into J plus 1. So energy of J plus 2th level, J plus 2 level is equal to B into J plus 2 into J plus 3. So for a transition from J to J plus 2, the delta E would be delta E is equal to J to J plus 2, which is equal to E J plus 2 minus E J, final minus initial. So E J plus 2 is equal to B J plus 2 into J plus 3 minus B J into J plus 1. We are calculating this thing. B is taken outside. J square plus 5J plus 6 minus J square minus J. We will get B into J square and J square will be cancelled. 5J minus J, 4J plus 6. If we are taking 2 outside, 2B into 2J plus 3 would be the delta E for the transition J to J plus 2. So for a transition J to J plus 2, we require an energy of 2B into 2J plus 3. Now we take these transitions and find how much energy is needed for each transition. So let's first consider 0 to 2 transition. So 0 to 2 transition means J to J plus 2. So here J is equal to 0. J is equal to 0. J plus 2 is equal to 2. So the energy required for 0 to 2 transition is 2B into 2J plus 3. In the place of J we put 0. So that we get into 3, that is 6B. So 6B energy is needed for the transition of 0 to 2. Like that we will find for delta E for 1, 2, 3. So J2, J plus 2. So J means 1. So in the place of J we put 1. We will get 2B into 2 plus 3. In the place of J we are putting 1, 2 plus 3. That is 10B. 6B, 10B. Next delta E 2 to 4. 2B into 2 into 2 4 plus 3 7, that is 14B. So we got 6B, 10B, 14B, which indicate there is a difference of 4B always. Now let's consider delta J minus 2 case. Delta J minus 2 means the transition is from just opposites 2 to 0. So here J is 0 and J plus 2 is 2, but just opposite of what we have seen just before. So the energy is same 6B but in the opposite direction or in a negative manner. So let's see how we plot these energies. So first we are considering delta J is equal to 0, which is the Rayleigh line. And Rayleigh line, compared to Rayleigh line, we have to see this Stokes and anti-Stokes line comes in left or right side. So Stokes means delta J is equal to plus 2. Anti-Stokes means delta J is equal to minus 2. Now we know that for Stokes lines, energy scattered is less than energy of incident radiation. So if Rayleigh line indicate the incident radiation, where mu bar I means energy of incident radiation. If mu bar I is the energy of Rayleigh line or energy of incident radiation, Stokes line is less than that. Less than that means Stokes lines comes in the left side, because it is smaller than this mu bar I energy. And Stokes line means delta J is equal to plus 2. In plus 2, which are the transitions possible? 0 to 2, 1 to 3 and 2 to 4. And for 0 to 2, we know that the energy required is 6B. The energy shift is 6B, and this one 10B, then 14B. So for 0 to 2 transition, which is the first Stokes line transition, we get an energy at a 6B smaller compared to mu bar I. So 6B line will come here. This is the 6B difference. And for 1, 2, 3 transition, the line comes at a 4B difference. Means it is at the position of 10B. If this is 6B, this is 10B, but the difference is 4B. And next line will come as like this, 14B, and the difference is 4B. Then this line is more lengthened because it is the most possible transitions. Number of transition is high in that manner, so the intensity is also high. So just opposite we will see for delta J equal to minus 2 case, that is anti-Stokes lines comes in the right side of the mu bar I. Here also we will get the first line as 6B, second line in 10B, third line in 14B. We just draw the lines like this because commonly rotational Raman spectra will look like this. There is a particular trend in the intensity. Just some are smaller, some are higher, like that. So what we can understand that compared to mu bar I, the first line comes at a difference of 6B in both direction. First line of anti-Stokes and first line of Stokes line comes at a difference of 6B, and all other lines have a difference of 4B. So this is how a rotational Raman spectra look like. Rotational Raman spectra. So mu bar I is the initial radiation, B is the rotational constant, 6B is the gap between the first line, and 4B are the gap between other lines. And in this section we have to cover one more topic, that is vibrational Raman spectroscopy, which is the last topic of this chapter. Vibrational Raman spectroscopy. Here first we have to study the gross selection rule, which means which are the allowed transition. That is delta V is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Transitions are possible in vibrational Raman spectroscopy. And the most population is present at the ground state. We are considering until 0 and plus or minus 1 because other than ground state, from first level, second level, their population of molecule is very low, so very less chances of transitions of plus 2, plus 3, etc. Very less number we can see. That's why we are most considering the 0 and plus or minus 1 transition. So if delta V is equal to 0, the energy for that transition delta E is equal to mu bar I, that is the incident radiation only. If delta V is equal to plus 1, the energy required for such type of transition is mu bar I minus mu bar 0, where mu bar 0 is the fundamental vibration energy required for fundamental vibration. Fundamental vibration means very fundamental, that is 0 to 1 transition. And we also know that mu bar 0 is equal to mu bar into 1 minus 2xe. This we have covered in the chapter of vibrational spectroscopy. And this mu bar is obtained from the vibrational frequency of the molecule, where vibrational frequency mu is equal to 1 by 2 pi root of k by mu, where k is the reduced mass, k is the force constant and mu is the reduced mass. So this is the mu, that is vibrational frequency. Mu bar, the energy corresponding to vibrational frequency mu bar is equal to, we know that mu bar is equal to 1 by lambda. And mu is equal to c by lambda. So to make mu to 1 by lambda, we have to divide this thing with c, so that we get 1 by lambda, which is equal to mu bar. So dividing mu with c, we get mu bar. So mu we already know, 1 by 2 pi root of k by mu divided by 1 c will come, which will come here. So this is the mu bar. So this mu bar we will put here. We get mu bar 0, 1 minus, using mu bar into 1 minus 2x equation. And once we get the mu bar 0, we will put this mu bar 0 here to obtain the energy required for a delta V plus 1 transition. For delta V minus 1 transition, the energy required is mu bar I plus mu bar 0. So if we draw the line, so this is the mu bar I incident radiation. Mu bar I minus 0 comes here. That means delta V plus 1 line come in the left side. Delta V minus 1 line come in the right side. This is mu bar I plus mu bar 0. And this is mu bar I minus mu bar 0. This is the only thing we have to study in vibrational Raman spectroscopy. Just study this part.